All right, honors calculus. We are going to wrap up the course with our last bit of work with integration um, for this term. And what I'm going to do is hit a few points in section 4.4 that I just want you to sort of hear about. You're gonna experiment, well, not really experiment, but you're gonna practice a little bit with it in your homework. But the brunt of this final homework set um, and final lecture is actually going to be dealing with some more complicated integrands. So that's actually in section 4.5. So in your notes, if you're following along with me in the PowerPoint, I put that all together into one last guided notes. And you will notice that your final homework assignment, which is not due until the afternoon of Tuesday, so that you have a chance to ask me questions if you have any. That final assignment covers both sections, 4.4 and 4.5. So you'll see you have a couple of problems in each, and your final quiz, which will be due on the day of your senior exam, along with your optimization problems. That final quiz will also cover this stuff, just FYI. Okay, so in section 4.4, in terms of your homework, some of the homework, actually more than half of the homework problems in section 4.4 cover things that I taught on the prior video that's up on YouTube. So you might need to go refresh yourself. Things like using the mean value theorem to find the average value for a function. And using definite integrals to find area under a curve. Really, just the definite integral is equal to the area under a curve. So I don't know if you need to see more with that. But I covered that in the last video. So just FYI, if as you're starting your homework, you're thinking, oh, she didn't talk about this. It's in the last video, the one that is labeled, I think, 4.4 video 1. So you can go look at that if you need to. So I'm going to pick up here with the tail end of section 4.4. And it introduces just two things that we're sort of glossing over. One thing is, so just to refresh, if we're looking at a definite integral, so this is a definite integral, and I'm looking at it from points A to B, right? A is my initial point, B is my final point. Just as a refresher, if I were going to solve or evaluate this, I would take the integral, right? I would integrate this function, and then I would plug in value B and subtract from it the function at value A. And so I'm going to get generally a numerical answer. You can have some starting point. Typically it's 0. We'll say A. And you can go up to just a variable. Instead of so remember B would be a number. Like I would integrate from like 0 to 10, for instance. You can start from a number, let's say 0, and just go up to a variable x. And so this is another way. Just sometimes it has we'll see in a minute, but sometimes it has its uses. So this is another way we see definite integrals notated or written. Nothing about how I solve it will look different, except instead of putting a number in for that final point, I'll just put x in, or whatever variable they would give me. So again, I'll do a practice problem here in a second with that, but this is one thing that's a little bit new. I didn't really show you that in the last set. The other thing that is new is, I wrote it down here, but this is the second fundamental theorem of calculus. So you have it all typed out in your notes. The second fundamental theorem of calculus. Now you can actually do some pretty complex stuff with this, and we're not going to. But the second fundamental theorem of calculus says, let me read it in words, if f is continuous on an open interval, and that interval contains the value a, which would be usually your starting point, then for every x in the interval, the derivative of the integral from a up to x is equal to this function f of x. We know that the integral is the antiderivative, right? So the derivative of the integral should give you this original function that you're integrating. It's kind of restating what I've already said. So there's nothing really particularly new here. Again, it has its uses that we're not getting into because I dream of having more time in this class, although I'm ready for summer just like you. If we had more time, we would do more with this. It comes up later. So I just wanted to say it because I think a lot of you will go on to take a college level calculus course in the next year, maybe 2 years. And this is something you might see come up again. So let's look at a practice problem more with this idea. Just if I use an x instead of a b value. So here's the first problem in a PowerPoint. It says evaluate the function f of x is equal to the integral of the cosine of t with respect to t from the value t equals 0 up to x, okay? And then it would say evaluate that at these values. X is equal to 0, pi over 6, pi over 4, pi over 3, pi over 2. So you have a couple of homework problems that do this sort of thing. Okay, so what do? Mathematically, I mean, it looks exactly like what we were doing last week. So I'm just going to go integrate this. So the integral of the cosine of t is the sine. And I want to evaluate that from x is equal to 0, or up to x. Sorry, from 0 up to x. That's what I'm trying to say. So I'm going to plug in. So I say sine of x minus sine of 0. Sine of 0 is 0, so I end up with the sine of x. So this is my answer, like for the function. So I guess I should have written this out in front. My function is equal to the sine of x. Instead of, if this were some value like pi, I'd have a number answer instead. Now, they asked me to evaluate that at these points. So all I do now is plug these different points in for x. So I could say the sine of 0, and that is 0. Sine of pi over 6, and that is, I have to cheat, this is a shame. I need to review if I ever teach this again, who knows, I need to review my radial form. I'm used to it in degrees. Sine of pi over 6 is 1/2. Sine of pi over 4, oh, that one, I know, square root of 2 over 2, and so on. So I'm running out of space, but I would plug in all of these things all the way up to the sine of pi over 2, which I do know that one off the top of my head, is 1, right? So I'm just, to get these different numbers, I'm just plugging this value in. I can think of this conceptually as like an accumulated area. So if I had a graph for my sine function, starts at 0, works its way up. It's like, these are my different points. So this is the area, like for pi over 6. And then as I work my way up to, I don't know, this is pi over 4, let's say. And so I'm building more area all the way up to, I went in this case all the way up to pi over 2. And so I've accumulated an area of up to 1. So as I'm changing these values for x, we see my area accumulating. That's one way to think about it. But the point is, if you have this x as one of your endpoints, you just put in x. That's all you do. And then they might ask you to evaluate it at certain points, and all you do there is plug in your values at the end. Okay, so that's a way of using this concept. Let me show you a real quick second fundamental theorem of calculus. I think I gave you 2 to try in your homework. Again, not something we're using very heavily. Okay, so the one that's in the PowerPoint, our practice problem is evaluate the derivative of the integral from 0 up to x of t squared plus 1 with respect to t. Okay, so we want to know what's the derivative of this whole thing. Okay, like if I was trying to take the derivative, I don't know. It's kind of complicated. I could take, one way to do it would be to integrate this, put in the value for x, then take the derivative of that answer, and we will get something. Or I can say, well, I know by the second fundamental theorem of calculus that the derivative of some integral is equal to the original function of under the integral, or in the integral that I'm integrating. So what am I integrating? I'm integrating t squared plus 1. Now I'm going to put in, x if I'm doing it with respect to x. So my answer is x squared plus 1. That's it. So I'm just, again, I didn't do the proof for this. but I'm trusting this fact and just saying, well, then the derivative must be equal to the function. And that's all there is to it. So, you know, again, how is that useful? For future things, it could be where we aren't doing a whole lot with it. Okay, so I want to jump into section 4.5. And section 4.5 introduces a way to handle more complex integrals. And I used to, when I first learned this, I loved it because it felt like doing a puzzle to me. We're not doing everything with it. I just want to introduce the concept, so you're just working with problems in the very beginning of the section, and we'll call it a semester. But this is kind of like doing the opposite of the chain rule. So when you learn the chain rule, I know you reviewed this with me. I didn't teach it to you originally, but when you learn the chain rule to take a derivative, you said the derivative of, like, sort of a multi-layered function. I'm probably not using the correct math terms, but to find the derivative of a function like f of g of x, this would be equal to the derivative of the f function. You keep that g of x there, and then you do like the derivative of the inside function, right? So this is your outside function. And this is your inside function. And then this is obviously the derivative of your inside function. So, like as a reminder, if I had x squared plus 1 squared and I wanted to find the derivative of that, I first take the derivative of like this whole thing, so the outside function, so 2 times x squared plus 1, so I'm keeping that inside function, right? So I took the derivative of the outside function, I keep the inside function intact, and then I take the derivative of the inside function, which is 2x, and I could simplify that out, but or clean it up a little bit, but that's what I'm doing, right? So to integrate a more complex function, like, I mean, again, this one I can multiply out and use power rule, but let's sometimes it's not that easy to do. So let's pretend I can't. To integrate a more complex function, we do this in reverse. So we would say the integral of f of g of x, g of x dx, I'm integrating this, is equal to f of g of x plus c if it's an indefinite integral. If it's a definite integral, they're going to give you these endpoints, right? And you just plug them in at the end as we normally do. Now, like, there's nothing wrong with this. There's a lot going on with f's and g's and x's and whatever. And so we can rewrite these things. We can use a u. You can use any variable you want, really. But the textbook and when I learned it years ago, we use u for whatever reason, just to substitute. So this is called change of variables. So we're going to let u, so g of x would be equal to u, and g primed of x would be equal to du. So we could say the derivative, I'm sorry, the integral, oh my gosh, the integral of f of u with respect to u, right, which is, I'm just substituting in here. Remember, u is g of x, du is g primed of x, is equal to of u plus c. So this is an easier way to write it. Now, I'm expecting as you're watching and following along and hopefully taking notes that this is probably still a little bit, it's not making sense yet. And that is okay. What I want to do, actually, I'm changing it as I go. I want to talk about, if you're following me along in the PowerPoint, I skipped the slide that said recognizing the pattern. I want to talk through the steps and then just keep practicing with these so it makes sense. So we'll recognize the pattern after I talk through the steps. So if I'm trying to integrate with all this u's and g's and x's and whatever, there are some steps we can follow. And I'm someone who needs just, I like to be told what to do. Math involves a lot of creativity. I hope you have a sense of that from your high school math career. Just you really have to take creative approaches to problem solving. But you still need those like nice fundamental, I'm getting on a soapbox here, but you need those nice tools, right? And a clear fundamental understanding of what those are. So this is one of those things where when you integrate, like there can be a lot of creativity that's involved in how do I approach this problem. The more complex they get, often the more ways there are to do them. And what they stand for, and it's just, there's a lot of creativity. However, when you're first using this rule, it's nice to have the step by step by step. This is what you're supposed to do. So let's do that. So I'm on the slide that steps for the change of variables. Okay, so first step is you're going to choose a substitution where u is equal to what we would have called g of x in the old formatting. This is usually your inner part of the composite function. You know, again, there's some creativity. Usually this is how it works. You'll see as I go. That's we're not going to see like the exceptions to the rule yet because we're just doing the basic stuff. There are exceptions to that rule. Okay, so first you choose that. Then you compute the derivative of that. So du is equal to g prime of x with respect to x, or whatever the variables are. So you just take so you say, I'm going to let u be whatever part of the function. Will make sense when I do it in a minute. And then du is the derivative of u. And then you don't do that, you rewrite the integral by substituting basically your u and your du. So you'll see me do that in a minute. Then you find your resulting integral, so it'll be much simpler to integrate. You want to get it into a place where you can use either some of our basic trig stuff or power rule to integrate. And then finally, once you have your integral, then you replace that u by whatever you said g of x was to get it back sort of in its original formatting. To get your antiderivative in terms of x. And as a final step, you could always check your answer. I get sloppy about that, but one should check one's answer. So if you want to check your answer, you get an answer, take the derivative of that answer and see if it's the thing you're supposed to be integrating. Okay, so let's do some practice with that. I'm going to switch out markers here. Let's do some practice with that. So now I'm going to go back to, as I'm popping around, I'm going to go back to the second slide, which was recognizing, not the second slide, I'm sorry, second slide with this, which was recognizing the f, g, x, g prime x pattern. So let's look at this. Okay, so we're going to integrate x squared plus 1 squared times 2x with respect to x. Now, again, our old way, like this one, I could expand this out, right? So I could take x squared plus 1, square it, then multiply everything by 2x, I'm sorry, and use the power rule to integrate it. I could handle that. But let's do it this way. Let's try it this way. Okay, so first step, choose a substitution. U is equal to g of x. Usually it's an inner function. I'm going to say, I'm squaring this thing. This looks like my inner function, x squared plus 1. I might not know, like, you know, I might not be confident. Just pick something and try it and see what happens. So I'm going to let u be x squared plus 1. Now I take the derivative of that. So du is equal to 2x, and I did it with respect to x. So you're always going to put that dx term on there. What does that mean? Well, dx, I'm going to solve for dx, and I'll show you why in a minute. Dx is equal to du divided by 2x. Sorry, I can't even read there's a little glare, I can't even read. Sometimes you need to use this, sometimes you don't, so I just did it. Okay, so let's substitute. So we put in our stuff. So u is x squared plus 1. So here, sorry, we've gone through this. We did u, found the derivative of u. I'm on step 3, rewriting the integral. Okay, so I said u is equal to x squared plus 1. So we have u squared. Now I have this funky thing, 2x dx. Well, guess what? 2x dx is du. So I'm just going to write it as du. Sometimes you have to use like fraction stuff out. Again, I didn't have to here, but so du, and then I'm going to integrate that. So I'm going to say, okay, well, with respect to u, that becomes u cubed over 3. This is an indefinite integral, so we need to still go in and add that plus c. So I did step 4. I found the resulting integral. And then step 5, replace u by what u was. So u was x squared plus 1. So I have x squared plus 1 divided by 3 plus c. That is my answer. So again, go pick your u, take the derivative of u. I tend to solve for dx on the side. You may or may not choose to do that. You will see why I might have again in a few future problems. Substitute, integrate, rewrite with your original values. Let's try another one. Oops, I'm dropping stuff. All right. The second one on that slide was 5 cosine 5x dx. We want to integrate this. Okay. So again, I am going to pick my u first. U's usually your inner thing. So I'm going to say this, like this 5 is some constant I could pull out, right? So I'm going to pick 5x as my u. So I'm going to say let u is equal to 5x. What is du? Du is equal to 5 dx. And then I am going to, sorry, I'm just having a moment where I'm thinking I might need to present something to you. Then I'm going to go and substitute in. Okay, so I'm taking the cosine of u. Du is 5 dx, which I've got here, right? 5 dx. So with respect to u, and that's it. This is written would be the same thing as this if I put in what these terms meant. And so now I'm going to integrate this with respect to u. The integral of cosine, sorry, is sine. And I'm going to add my plus c. And then I need to put in what is u, right? So u is 5x. So my answer is sine of 5x plus c. Okay. In a bad teacher moment, I just had a moment where I thought this notation might be confusing to you. What I'm doing here, and what we always do with this, is we use the Leibniz notation, which at the beginning of me teaching, I remember noticing I'm much more comfortable with Leibniz. It's the more formal calculus notation. So in college, like for me, it was like exclusively used in college. You people, when I came in, you were using more Newtonian notation, which is sort of ironic since I'm a physics person. I can't stand Newtonian notation. And so I stuck with that because I didn't want to confuse you. But now at this moment I'm realizing I probably confused you. Because we're getting into this more formal calculus, we need to be using really the Leibniz notation. So when I have u is equal to 5x, I'm taking the derivative of it with respect to x is equal to 5. And then what you see me keep doing is like getting du by itself. Okay, so that's why I keep tacking this term dx over on the right side when I'm taking the derivative. That might be condescending. You might have been like, you had that, you knew exactly what I was doing the whole time. But some of you really are using that Newtonian notation. Might have been like, what is she doing? So I'm just taking the derivative, and this is taking the derivative with the Leibniz notation. Okay, sorry. So let's do a few more practice. This is getting to be a long video, I see, but I'm going to try and squeeze it all in. We're just doing I'm on the last slide. Just going to crank through some of those practice problems. Again, just going through the same process. Okay, so number 1 has a square root. It says the square root of 2x minus 1 dx. Okay, so I would rewrite this personally as 2x minus 1 to the 1/2 dx. All right, so I'm going to let u be my inner function, which is 2x minus 1. du is equal to 2 dx. Now, here this is, so like this dx doesn't, there's no 2 there. So here we have to be a little bit, this is where we'll have to substitute a little bit differently. Dx is equal to du divided by 2, right? I'm just basing that on this. So when I go to rewrite my integral, I'm taking the integral of u to the 1/2 power with respect to u. So I can't just put in du. I need to put in du over 2 because that's what dx is. Again, because I didn't have like a 2 out here to cancel like I did for the other ones. And so when I go to integrate this is just a 1/2. It comes out. It's a constant. So if you want to write it again, I could do it like that. Okay, so this ends up being 1/2 times u. When I add 1 to this, that becomes 3/2 divided by 3/2 plus c. Whew, that's getting sloppy. And so this ends up being 1/3 u to the 3/2 plus c. Okay, so my final step, sorry, if ever I end up teaching out of my basement again, I'm buying a new board so I have more space. This becomes 1/3 u, which is 2x minus 1, to the 3/2 plus c. That's my final answer. Again, you pick your u, find the derivative, do some substituting. Here I had to be a little bit more careful with that dx term. Let's try number 2. I don't know if we need to do all 5, but let's go through a couple more. All right, number 2 on that final slide. I am integrating, it's almost the same thing. I am integrating, this was the one I put on your quiz accidentally. And then I was like, wait a minute, we have to be doing this thing to, I was confusing quizzes and, oh, it's a mess, so I'm sorry about that. Okay, so we're integrating x times 2x minus 1 dx. Okay, so this one could be complicated. Again, I would go rewrite. So I'm going to say x times 2x minus 1 to the 1/2. I like it like that, dx. Okay, so if I'm looking, I still think like this is my inner function, right? So I'm going to say u is equal to 2x minus 1. Du is equal to 2 dx. If I had to solve for dx, dx is equal to du over 2. Okay, so that's all fine and dandy. Like I can go substitute and all is well, except then I would have x, right? I didn't take care of this. So if I go substitute right now, I would have x times u to the 1/2 times dx, which can become du over 2. Well, then like, what do I do with this thing, right? So what I have to do is I have to solve for x in terms of u. So here's some of that creativity. So if I go look at what I have, well, look, I can do that. If u is equal to 2x minus 1, then u plus 1 is equal to 2x, right? So x is equal to u plus 1 divided by 2. So let's go put that in here. This becomes the integral of u plus 1 divided by 2 times u to the 1/2 du over 2. So I have a 1/2 times a 1/2 I can pull out. So this becomes 1/4 times u to the 1/2 times u plus 1. If I pull out, these powers are gone, du. And now I can see I'm going to be able to use the power rule. This is 1/4 u to the 3/2 plus u to the 1/2 du, which becomes 1/4 times u to the 3/2 becomes u to the 5/2 divided by 5/2, so times 2/5, plus u to the 3/2 divided by 3/2, so 2/3, plus c. And there it is. Now I'm running out of space, so at this point, I mean, this is great. At this point, I just need to put in, instead of u, 2x minus 1, that's what u is, into each of these terms. And there you have it. So that's about as long. I didn't do anything beyond that for you for homework. Most of them are shorter than that. But that's about as long, not as we can get, but as we will get for this end of your senior year. And let's do, well, I don't know which one we should do. Maybe we'll just keep cranking through them. Let's do the trig one to see that. All right, so here's a trig one, number 3. The integral of the sine squared 3x times the cosine of 3x with respect to x. Now I would rewrite this a little bit. Sine squared 3x is the sine of 3x squared. That helps me see like the inner function a little bit better. These two things are the same, you know. Times the cosine of 3x dx. Okay, so then let's go for it. So I'm gonna say u. I'm thinking this is my inner function. So I'm gonna say u is equal to the sine of 3x. Du would be cosine, if I take the derivative of that, cosine of 3x times the derivative of the middle, 3, for inner, with respect to x. Okay, so when I go to substitute, I'm taking the integral of u, which is my sine of 3x, squared, and then cosine 3x dx, well, I'm almost there, but there's this factor of 3, right? So so du divided by 3 needs to go in here. Again, cosine 3x dx, there it is, but I have to divide by 3. Du divided by 3 gives me that. Okay, so then I can pull out the 1/3 if I want and integrate. It's integrate u squared with respect to u. So this ends up being 1/3 times u cubed over 3 with respect to u. I already did it. I don't need to say with respect to u, sorry. Plus c. And when I go plug in my values, 1/3 times 1/3 is 1/9. U cubed, well, that's the sine of 3x cubed, and then I need to add my plus c. And there we have it. Let's do a couple more. Almost done, almost done. Okay, number 4, the integral of 3 times 3x minus 1 to the, is it the 4th power? I can't read. 4th power dx. Okay, I'm going to call this my inner function. So I'm going to let u be 3x minus 1. Du would be 3 dx. Well, that's nice. I've got the 3 dx right there. So this one's going to be simpler. So when I go to rewrite it, I'm going to say I have u to the 4th. 3 dx is du. And let's integrate. This becomes u to the 5th over 5 plus c. This becomes 3x minus 1 to the 5th over 5 plus c. And there we go. So and this one turned out really nicely. And the last one, the final one, has what looks like a quotient. So I wanted to show you how I would do it. So here's my last one. Negative 4x divided by 1 minus 2x squared with respect to x. Okay, before I jump into that, I would lose the quotient notation. So I would rewrite it as negative 4x times 1 minus 2x squared to the negative 2 power with respect to x. That's my personal opinion. Then I'm going to let u be 1 minus 2x squared. Du then would become negative 4x dx. Well, that's nice, right? Look how much that simplifies. And so when I go to integrate, I have my u to the negative. I'm sorry, I think you might be hearing my family screaming upstairs. They're happy screaming. U to the negative 2 power du, which is negative 4x dx, so great. And so let's integrate that. That becomes u to the negative 1 divided by negative 1, so like negative u to the negative 1, plus c. So this becomes negative, we could just say 1 over u plus c, which is negative 1 over 1 minus 2x squared plus c. There we go. All right, so when you're going to do the homework problems on your own, again, just follow these 5 steps all the way. I didn't refer to them as well because I just got into it. But pick your u, take the derivative of u, rewrite that integration, substituting with your u's and du's properly. Remember, sometimes with that du, you have to put in a factor for the dx, so just be careful. Integrate, rewrite with what u is equal to. Voila, there's your answer. All right, and I will have office hours on Tuesday. Really, I'm available all week, so just let me know. But I'll have office hours on Tuesday. So if you have questions as you're working on the assignment, you can let me know, and I will help you out. And then you'll have one final quiz. So we'll go over, everything's kind of optional for next week because I know some people have AP testing, there's a lot going on. So just meet with me one-on-one if or as needed. I will post keys for this stuff once you finish it Tuesday afternoon. And then I will, on Tuesday afternoon, also send you your final quiz just to check in how you're doing with these things. And when you finish so this week on the agenda, you're going to finish your homework for Tuesday, and then finish your quiz and your optimization of household objects by Friday at the latest, and you're good. That's it for the course.